Since we have already created a geometry, and our parameter is the thickness of the aluminum cell, and it is 0.8 mm thick. We'll use component system, this analysis system from Fluent, from this toolbox, and drag and drop it into the this workbench. This project schematic will open the mesh, and we'll have to choose the Fluent meshing system. We'll use watertight workflow geometry to mesh the battery system, because it will be very handy. The first thing we need to do is to import the geometry, put the units in the We'll not be adding any local sizing in the system, and we'll generate the surface mesh. So in the surface mesh, the parameters that we need to add is the mean parameters is the maximum size is 0.4 mm. Sorry, minimum size is 0.4 mm, the maximum size is 7.5 mm. We have to adjust the growth rates to 1.2. Size functions will be curvature and proximity, sorry. And other things are, we have to check for intersection. We have to invoke the zones. We don't have to, this should be no, this invoke zone separation by angle. And invoke quality improve should be yes. Auto assign the zone types yes. This improvement skewness limit is point 0.9 value, and the maximum angle is 40. So this is how this surface mesh will be generated. And in this, okay, sorry, in this surface mesh process, the surface mesh will be generated. So we'll have to describe the geometry. After that, the geometry type is that it consists both fluid and liquid, solid liquid regions, and voids also. It won't be having any cap openings to extract the fluid regions, but it has to apply the shear topology. And after creating described geometry, I have to apply the shear topology also. The maximum gap distance is zero point 0.2 mm, and the shear topology methods will be done. And after that, we'll have to update the boundaries. So the boundary is that our inlet is this part that we can see in the screen, and the outlet is this part. Outlet will be pressure outlet, atmospheric pressure outlet, whereas inlet will be our fan velocity inlet. And there are two parts which are walls, which are positive and negative tabs, which we will which we will be choosing to complete our electrical circuit. The our estimated fluid region is air fluid, or simply air region, which is outside of the aluminum cell and inside of this box. So this is our fluid regions. Now, after that, we will be creating the regions. There are different regions. So aluminum 2 is our solid, cell is our solid, insulation 1 is our solid, insulation 2 is our solid. This are polyamide tapes, neck tab and post tabs are our bus bars, and outer ear is our fluid, and our support will be solid, which is wood, and which is used to approximate ear and some woods also. So I we created a boundary layer. And the smooth transition one, transition ratio is 0.272, and number of layers is 3. Numbers of layers are 3, and growth rate is 1.2. So approximating from this surface mesh, we'll create the volume mesh, and we'll fill with polyhedra, because polyhedra has so many adjacent face. Number of adjacent face for polyhedra is more, and hence it will help to properly predict the this value, this simulating value, this field properties among the adjacent cells. So polyhedra is used. Growth rate is 1.2, and the maximum cell length is used as 9.15 mm, and polyhedral mesh angle is 30. Quality improved limit is 0.05, and this is how our value mesh is generated and meshing is done. And just after that meshing, we'll use okay, I can directly switch it from solution. I can save from this file and to write as a .mesh file, and I can use it whenever I want. Also, I can switch to the solution right away, but I'll not be doing that because I don't want to miss the simulation settings. because if a small parameter in this ANSYS macing is changed, it will affect the entire simulating environment. Uh, then we have with click the double precision and solid processor. Since I have only four, I'll use four, and our fluent is started. So this is our setup, where we will throw not throw, but we'll subject the miss file into. So in this solution phase, okay, so we'll be loading the maze. We'll be checking the maze, and we'll report the quality. Of course, we have to wait some few more seconds, because my computer, the computational power of my computer is very less compared to the load that I have given to this system. Okay, it is now generating the system, and it is making noise also. So this is our check is there are number of parameters. We have also in the fluent we have parameters, which is velocity as 4.3, but we'll give it in here. And other arts are volume statistics, phase area statistics, and check. Okay, I'll report the quality. And orthogonal quality is about point 0.2, which minimum orthogonal quality. So and aspect ratios are given. So our velocity formulation will be absolute pressure based solver and steady state. Since this battery thermal discharging process is inherently transient, but if this thermal constant is equal to this time constant that we use uh, to simulate the system, it will study will give very approximate results. We'll also on the gravity, and which will be minus 9.8 in the y direction. In the downward direction, our input and outputs are can be seen here from the blue and red rays. Now from the model, it is very simpler model, so I can. So I have to click the enable battery model CST coupling, which is a conjugate heat transfer coupling method. So as I have told you guys about this metallic part to make to join the cell into the wire, which I named as bus bars or simply post tab, neck tab. So these are passive zones. So I have to select the active zone, which is a cell component, and the passive zone, which is neck tab and post tab. After that, we'll have to select the electrical contact, which is to contact, and I can print the electrical system. And this battery model will automatically generate that number of batteries in series will be one, and number of batteries in parallel will be one, since it is a one by one battery, simply single battery configuration. Then this energy source, this CST related source is 0.9028 watt, and the total tap current is 2.13 ampere. So this has come from a research paper from the paper which is published in results in engineering and I'll provide the paper in the research in the description below. And the energy source is calculated as point 0 sorry 0.9 028 watt. So these are all we have to apply and initialize, and this will be all about the battery model. After that, I'll have to select the battery. The very first thing is year, and I will use the year parameters, sorry, year parameters in the which is already in the ancestry database. So these are all density, specific heat, thermal conductivity, viscosity, and electrical conductivity also. So in the solid part, I have the aluminum cell. For the lithium ion cell, I have conducted experiment, and of course in the same research paper I have published this data of density, specific heat, and electrical conductivity. Of course, nickel can be found as a bus bar that I have said This is a passive heat conducting element, and this density all are from the ANSYS database. Polymer tape we have used from the source that we have used in our experiment, which is a Kapton tape, and these all are the parameters of the Kapton tape. And there is a wood which we have used, and it is from the ANSYS database also. So in the cell zone conditions, there are fluid and solids, and you can assign the outer ear is the fluid, and the inner part aluminum cell, two insulating parts, two of these tabs are simply bus parts, and one is a structural support which is a wood. And in the boundary condition, the inlet is velocity inlet, and I have to parameterize this inlet. So I have created a function and named the parameter as vel, and these are the parameters. And for the thermal part, I have set the ambient temperature to be 295 Kelvin, which is the temperature of our environment while we were doing the experiment. And for internal part, there are all theirs, but outlet we have pressure outlet, and the only temperature, pressure outlet and temperature is given as 295 also, because it is also an ambient part, and our gauge pressure is 0. So these are all our parameters. After that, we will seek out for what we are doing. We are seeking the average temperature of cell to insulating part and the tabs as well as support whole the except aluminum all the systems, and which is the average static temperature, volume average static temperature. So volume average static temperature. Okay, so this is all about fluent meshing, and we have to run calculation, but in the initialization, okay, in the initialization hybrid initialization is done. And for calculation activities, okay, run calculation. Number of iteration is 600. Reporting interval is 1. And I can check the case here. No recommendation to make at this time. I can calculate it right now, but I have to initialize the system, and it will disturb the solution that we have got. There are of course graphs. There are no graphs. There are no plots. There are no animation in here, but we'll have it in the next part. I'll quit this right away, and it will be saving the miss file and everything that we have got. So this is the we'll talk about solution in the next videos, and also I'll say you guys discuss you guys about how I optimize this parameters with respect to the outer parameter, which is our cell average temperature, volumetric average temperature, and done everything. Okay.